Welcome to Data Science with EJD. In this video, we'll be talking about random forests for classification. As you already know, we are talking about machine data science in general. Under that, we have machine learning. Under machine learning, we have supervised, unsupervised, and reinforcement learning. So we are taking supervised learning for starters. And for supervised learning, we know there are two branches. We have classification and regression. So we've been taking the classification algorithms. So far, we've taken um, quite a number of those algorithms, including decision trees, k nearest neighbors. So now we are looking at random forest, which is nice to follow decision trees, right? Because, if you put trees together, you have a forest. So welcome to that random forest for classification. And our objectives by the end of this module, you'll be able to understand ensemble learning and bagging concepts. So the idea of ensemble is like aggregating things. So if to get a forest, right, you have to aggregate trees. That's the basic idea of random forest. So we want to describe the structure and working of random forest classifiers. Since we're talking about classification, interestingly, random forest can also do regression because you can have random forest regressor. So our focus here is on classifiers. Then we want to implement a random forest model for classification in Python. We'll analyze and interpret feature importance scores. So here, feature importance will be focused on a bit more. I mean, that this is the first time I think of coming across it. And the whole idea of feature importance is that you may have many features. So, I mean, we talked about the idea that when you come to machine learning or supervised learning for that matter, you have features and labels. So features are the inputs while the labels are the outputs. Okay, so not all the features, not all the inputs are equally important. Some are more important than the others. That is why sometimes it is necessary to highlight the features that are more important and then maybe eliminate the ones that are not so important so we can probably get a better model, most likely. So then we also retrain the model using top features and compare results after doing feature importance for sure. And we evaluate model performance using appropriate metrics. Okay. So, I mean, we've always seen that when you come up with a model, you want to be able to measure how the model is performing. All right, let's look at some conceptual foundations of random forest. So, I mean, it comes from the idea of ensemble learning. Ensemble means bringing things together, aggregating stuff. So, ensemble learning involves combining multiple base models to produce a stronger overall model. So, just like it's more when you bring one or more trees together, one or more decision trees together, then you get a forest, right? It can reduce variance. By the time you aggregate many models together, you can reduce variance, you can reduce bias, or even improve predictions. And here we have ideas like bagging. Bagging is short for bootstrap aggregation. Bootstrap aggregation, that's bagging. So bagging helps to reduce variance by averaging predictions from different bootstrapped data sets, right? That's bootstrap aggregation. Then we have boosting. Boosting reduces bias by sequentially correcting weak learners. All right. So if you have instances where you have we're talking about machine learning, and this is particularly supervised learning. So if the learning in some instances or in some situations is weak, right? Boosting actually helps to reduce the bias by sequentially correcting those weak learners. Then we have stacking, which combines multiple models via meta modeling. So meta modeling is like modeling of modeling, right? So anytime you see meta, like meta population, so meta population is a population of populations. And when you hear metadata in the data rules, right? Metadata, that's data about data, something like that. So meta modeling is modeling of modeling. So, and the whole idea of forest is that you have a group of trees coming together. So, random forest itself now, in overview, um, random forests is an ensemble of decision trees trained using bagging. You see, bagging is bootstrap aggregation, which helps to reduce variance by averaging predictions from different bootstrap data sets. So, random forest is an ensemble of decision trees, an aggregation bringing together of different decision trees trained using bagging with additional randomness introduced by selecting a random subset of features at each split, right? So random forest is used for both classification and regression, but here our focus is on classification, right? So then we have final prediction for classification. It's to have majority votes across trees. So you want to, it's more like you have an election and then you now have, say, maybe you have an election in a city, and in the city you have counties, so to speak. And so you now have election across. So a county can be considered as a tree, right? But by the time you put all the counties together, you get a forest. So at the end of the day, you want the highest votes across the counties, and you put all of that together to get your forest, and that way you can get better results. So the key advantages of random forest will be things like robust. It is robust to overfitting. So because you're aggregating many trees, you can prevent overfitting. It handles large feature sets very well. So if you have many features, you have many inputs. Random forest helps to handle that pretty well. Then it has built-in feature importance estimation. So in random forest, you can do feature importance easily. You can easily rank the features to see the most important ones. So let's talk about bagging and ensemble trees. The bagging process here, you generate multiple bootstrap data set from the original training data. So you have a training data, and then you can now bootstrap. You have different data sets of that data, right? And then you can train a base model, e.g., like a decision tree on each. So on each data set you have, right? You can now train a decision tree on each of them. Then by the time you're done with that, you aggregate all the predictions. So it's more like you're conducting an election, and you conduct elections across counties or wards as you have in some places. So by the time all the elections are conducted, then you aggregate all the scores to get the overall result. All right. So you have aggregation. So you at the end of the day you aggregate, right? Where am I? Okay, I think I need the space here to really get the picture. Yeah. So you aggregate predictions at the end of the day, where you have majority votes for classification. So you have small data sets fr got from the original training data, and then you now train a base model like a decision tree on each of them. Then by the time you're done, you put everything together, and you're most likely going to get a better result. So, and the result is that you have reduced variance and better generalization. All right. So let's look at some random forest specifics. So already we've seen ideas like bagging, like boosting, and of course stacking, right? Bagging, boosting, stacking. So random forest specifics. So first of all, random forest uses bootstrapped data sets when you talk about bagging. And bagging, of course, you remember is bootstrap aggregation. And this helps to reduce variance by averaging predictions from different bootstraps. So you have bootstraps across the board, and then you can then put them together later. So random forest introduces randomness at each split by selecting a subset of features. So and it grows trees fully without pruning or with a maximum depth if specified. Now, when we did decision trees, right, you saw the depth of trees, like how far you want the tree to branch out or something like that. That's the idea of depth. So it grows trees fully without pruning. So random forest allows all the possibilities available instead of decision tree where you should have a limit to how the things go. So having said all of this, can we look at a practical example? Of course, by now we already know that machine learning has a specific way it goes. Number one, you have a data set. You get your data set. The next thing is you want to clean up the data set to be sure it doesn't have any impurities, anything that can affect the outcome. Then when that is done, you train a model with your data set, right? So you split the data actually into a trained set and a test set. So you train you pick it, then you select a model, right? Depending on what you want to do, you select a particular model. Once you select the model, then you train the model on with your train set. And once that training is done, the next thing is to test the model with your test set. And when you do that, you now measure the performance of the model based on certain metrics. So that's like the standard procedure for all the machine learning things you'll be coming across. So it's standard like that. So the key thing is to just know your particular situation, know the kind of data you're working with, know the kind of model that will work with it. Or you may even have to try different models to now finally be able to choose what really works, right? So in this case, you're talking about random forest implementation in Python. Of course, scikit-learn is the most important, just like uh, Pandas is the most important Python library for data analysis. For numerical, if you want to do any numerical stuff, NumPy is the best for that, right? So for as far as machine learning is concerned, the most important library you'll be talking about is scikit-learn. That's why we'll be talking about it all this while. Okay, so you have scikit-learn data set. So you are using the iris data set once again. And then here we are using the random forest classifier. Mind you, random forest can do both classification and regression. So if we're doing regression, we'll probably be using random forest regressor or something like that. All right. So you have the scikit-learn model selection. Of course, this is a standard thing we always need to do because you always want to split your data set into train and test sets. Then you have also the metrics. You want to measure the performance of the model. So you need a classification report and you need to use the confusion matrix to take care of that. Then of course we need pandas because sometimes you need to do some data analysis things before you do your machine learning process. Then we need Seaborn and Matplotlib for visualization here. Okay. So the next thing is to load the data set. So here we say the data is iris. So we say data equals load iris. Then we can now get X. So we want to make a data frame out of that. So you have X is pd.data frame, uh, data columns data. So you have the feature names and all that. I mean, we can actually go the extra step to see what this actually look like, right? So let's do that. We want to first of all visualize what we are working with. So I'll cut this off. Okay. I'll remove this and okay, let me remove this and create new extra cells. So first we run this. Okay. We run this. The star says it's running, and when it's done, we have that number. Good. So the next thing is now I want the reason why I cut that off is I want to see this X now. This X represent the features, right? So I run that, so it shows us the usual iris data set we've always seen, sepal, length, sepal width, and all of that. And then we want to see the target. So what is the target in this case? What is our focus? So the target is the target talks about the species and they are labeled zero. The first species are labeled zeros, the second ones, and the third twos, like that. Then I can now bring that in which I removed. So here now, so we train the data set. So train, so test, split, and this is a standard procedure to go like we've always been doing since this whole thing started. So we have the X train, X test, Y train, Y test equals train, test, split, then X comma Y test size. It means we are testing with 30%, meaning we are training with 70% and testing with 30%. And the random state is 42 to ensure we always get the same results. And here, this is where we train the model. So first of all, declare the model. We are using a random forest classifier. So how many estimators? 100. So it's more like you have an election in a city and there are 100, you have 100 wards in that city. That's what n estimators represent. So how many trees or something or bush traps or so are you working with? And then again, you have the random state thing here, which is 42 to ensure the result doesn't ever change. Then you have model fit now. So you now fit the model to the trained data, both X and Y. And then you can, so once this training, so we do the train and test split. So this is necessary here to now train the model. And once that is done, you now want to evaluate the model. You want to so put your test value for the features so that you can actually get a predicted value for the target, right? So, and there you can now print classification reports. So it just gives you classification reports for Y test, Y pred, target names. So it gives you the target names. And then you can now do a confusion matrix to represent this whole thing. So we can do all this step by step, but we can also do it in one blow, right? So all this now, just run and then you get your results. So again, we have, you can see all this, the accuracy, first of all. So you see from average, so when you do average for at the macro level, you have 1.0 all through. So, I mean, everything is 1.0, meaning that you have a perfect situation because of the nature of the data set. In most situations, in most real life situations, you hardly get this. But the structure of the iris data set is pretty simple to follow. It's kind of linear. There are no complexities per se. All right. So here we are, so you can see that uh so for the confusion matrix now between Setosa, oh, okay, Setosa you have 19, versicolor 13, and all of that like that. And elsewhere you have all these zeros. Okay, so now, and from the values, you can see all the precision recall and everything shows that we have a perfect situation here. The accuracy, so the classification is perfectly done, right? So now let's talk about feature importance. Now, maybe the feature importance may not make so much difference because we already got a perfect situation. So if you have a perfect thing like this, feature importance may not be necessary. But for the sake of learning, I'll still go to feature importance. Now, feature importance is very good if, for instance, you got your accuracy to be like 0.5 or 0.56 or zero point 0.6, something low, and you want a better result. Even if you get like 0.8 and you want to see if you can go to 90 if you remove some features. That's where feature importance now comes into play. And for feature importance, you can have something like Guinea importance. And here, so what you're trying to do is you want to sort all the features you have. So you have this variable name importances. So from the model, you just a model dot feature importances. So you want the important features, right? Then the feature names, you have the x dot columns. For forest importances, you have PD series importances, index feature names. Then you sort the values in descending order. So if you want it to be ascending, you can also change it over, right? Um, then you can now plot that to see which of the features are really important. So with this now, look at this here. Okay, I guess let me reverse this. I want it to actually be ascending, right? So ascending true. So I want, yeah. So here you see that the petal width is the most important feature in the model, followed by petal length. Sepal length and sepal width are not so important. So if you want to eliminate any of this now, you can eliminate these two and work with these two to see if, but the model is already excellent. So this is just an exercise that we just need to do. In case you have another data set, this is really important. In case you don't have you already got a perfect classification. So, but this is necessary just for the to learn. So you now see the feature importances, right? So the ranking, sepal length comes first. Uh, all right, petal width, just like we've seen, petal width is 0.43, petal length is 0.41. So this talks about the magnitude of their importance, just like we've seen on the graph already. So if without even seeing these numbers, you can already see petal width and petal length are the most important features in this model. So then with this feature importance, now you may now want to go back and do the model again with these important features. So model refinement using top features. So you can now choose to select top end features. So for me, I want to select two of the features now, right? So since we know that the most important are petal width and petal length, so we can just pick those two and forget about the other two. That's what we are doing there. So x top is equal to x of top features. So we run this. So that is done. And then the next thing is we train with the top features now. So we go through the same process, X train top, X test top, and then we do all the train test splits, X top, Y, blah, blah, blah. Exactly what we have done before, the same process. And then we train, we feed the model to the data, and then we do our prediction. And there we have it. Okay. So the next thing is you want to evaluate all this we've done before. So now we do this. So now now you want to do the evaluate reduced model. So now you're only using two features, right? So you see that uh in this case now, I mean, this is to be expected because even without feature importance, we already got an accurate result. So you see that in this case, you can see the results are reduced. So you see up there we had 1.0 everywhere, but here we have some of the results getting bad, getting not so good, 0.69 everything. So and you see the accuracy with all features is 1.00, whereas accuracy with top three features, now it's actually top two features. I chose top two features, right? So accuracy with top two features gives 0.73. So the performance is lower. So it means that it's better when we have all the features, right? So with top two features, the performance is now 73% instead of the 100 we had before. So let me use top three now and see what happens. So if we use top three features, we can expect that the result will be even better than using top two features because it's perfect. Yeah, you can see the result has greatly improved with top three features, right? So the result has increased. So for this particular iris model, it's better use all the features, right? Since there are not even many in the first place. But this is just to describe the process. So if you got low values, then you can do feature importance and probably that can give you a better result. So then we can do cross validation for comparison, right? So cross validation. So you want to see, okay, cross validated accuracy for all features 0.9667 for three features. Then for cross-validated accuracy for top feature 0.94. So you see the all features will still do better than this. Now cross-validation comes in if you don't, even after using all the metrics, you still don't get the kind of thing you should get. So you now need to do cross validation to be very, so it's more like going the extra mile to find out what exactly what to get a convincing result as to the performance of the two approaches, right? So cross-validated accuracy is 0.96, that's 96.67%. And then with just the top three, you have 94%. So you see that it's still better to have to have all the features, or at least as many features as possible, as far as this particular data set is concerned. So in summary, with summary and insights, right? We have some going by the steps. Now we have ensemble basics. You combine multiple trees using bagging. That's bootstrap aggregation. Then you have random forest, which added feature randomness to improve generalization. The implementation, we have a trained random forest using scikit-learn. Evaluation used metrics like accuracy and confusion matrix. Feature importance, identify key predictors. Refinement, retrained model using top features and compared performance. Those are the processes we have gone through. So you try the first time. So we already got something perfect. So we didn't need to do anything extra as far as this iris data set is concerned. But for most data sets, probably you get a result and then it's not so, maybe you got 80% and you want to say, okay, what if you drop some features, you might get something better. So that means that those ones you dropped are not really important to make decision with the data set. Okay, for key takeaways now, random forest is a robust, accurate ensemble method for classification. Bagging and random feature selection make it less prone to overfitting than a single decision tree. Okay, so by aggregating many trees, you can get better results, right? So feature importance allows us to interpret and simplify the model. Retraining with top features can yield simpler models with minimal performance trade-off. In this situation, that's not true, but I mean, in most cases, you can expect that. So possible extension to this process we've done now. So you can try this same pipeline, this same thing we've done. Thankfully, all my data sheet, my code sheets, you can find it by following the link in the description box. So you can download this and then use the same thing now. Instead of using the iris dataset, you can then use a breast cancer dataset or Titanic dataset that is also available. You can get it from scikit-learn or from Seaborn or any of that. All right. So try this pipeline on another dataset, which is breast cancer dataset or Titanic. Then you can perform hyperparameter tuning using grid search CV. So, I mean, this is not necessary because we already got something perfect the first time we tried. You can explore permutation importance and sharp values for deeper interpretability if that's necessary. You can build a UI dashboard showing feature impact using Streamlit. So with that, we come to the end of this. Let me know how helpful this video is for you. Let me also know if there's something you'd like me to try out. If you have subscribed already, thank you. If you have not, please go ahead and subscribe and be sure to hit the notification bell so you can always get alerted each time a new video is released. My channel now has memberships. You can join as a member to get some special privileges. As already stated there. Then be sure to like and share so that more people can have access to this great content I have going on here. Till I come your way again, keep doing data right. Watch out for the next algorithm for classification under supervised learning, under machine learning. Keep doing data right. Bye.